All right, in the last few videos what we've talked about is how the principles of conservation of energy and conservation of charge relate to the movement of charge in circuits, current. In this video what we're going to do is we're going to talk a little bit about connecting things that we can measure in the laboratory, macroscopic measures, to things that are microscopic, things that we are unable to measure directly. And so this video we're going to try to connect the micro world and the macro world, particularly when we think about resistors and resistance, which is a quantity that we're going to define. So what we're going to introduce is this idea of what we, which is called conductivity. And conductivity is essentially a measure of how easy it is to move charges around in a piece of material. So I know we talked about electron mobility as being one of those things. Conductivity is another one which contains additional sort of pieces of information. Now, we refer to the conductivity with the Greek symbol sigma, which I know we've used before in thinking about charge per unit area. And it just turns out that in physics we have so many different kinds of things we keep track of that we run out of Greek letters to keep track of them with. So I'm sorry for the confusion, but it is the one that we commonly use. Now, when we talked about this idea of current, what we said was that that current is related to the charge of the charge carriers times the electron current, which is then related to the number density of charge carriers times the cross-sectional area of the wire times the average speed of the charge carriers as they move through the wire. And going a little further, we related that to the electric field through the electron mobility in this way. And so the conductivity is a collection of the material parameters. It's a collection of the things that are measurable, but they are all related to the charges themselves. So the conductivity is the product of the charge carrier, which is a measurable quantity, the number density of charge carriers, which is again a measurable quantity, it's known for materials, and the electron mobility, which is built out of things that are measurable quantities. So in a sense, this conductivity is itself a measurable quantity. It's something that we could, in principle, take some material and we could understand what its value is. But what that gives us is a definition of the current, which is definitely a measurable quantity. It's something that we can measure with multimeters, and relates it to two other measurable quantities and an inferable quantity. So something that is measured in the lab, or could be the conductivity, the cross-sectional area, and the electric field, which is not directly measurable. So we can get a relationship between the sort of micro quantities, like the current and the cross-sectional area, the macro quantity is the current and the cross-sectional area, and a micro quantity, which is related to the charge carriers themselves, but is also measurable, and something microscopic that has to be inferred from our measurements that we've conducted. Now, it's quite common for us to define a a current per unit area, so a current density, which is essentially the relationship between the current and the cross-sectional area. It tells you how much current per unit area is flowing through a material. And that is directly related to the conductivity and the electric field. And in advanced physics, we often think of this statement as Ohm's law, the relationship between the current and the electric field. So you might see this in some of your advanced electrodynamics courses in engineering, or if you're taking advanced physics courses, you might see that as well. But really, it comes down to the idea that a current passing a certain area has a current density. Now, the quantity itself of conductivity is one that has some pretty curious units. It is a coulomb squared second per meter cubed kilogram. And I don't think we'll ever expect you to worry about those units, but it's basically constructed from the units that you have here multiplied together, okay? Now, the last thing I want to talk about in this is how do we relate this all to something that we can measure in the lab that talks about how the actual circuit elements are constructed, or that is what their properties are that are measurable. So what we're going to do is eventually relate this thing to a thing that we call the resistance. And this quantity is one that often shows up when you have circuit elements that are put into circuits and they tell you a little bit about what we would refer to as the load, or sort of how much energy is needed to drive particular kinds of currents around in those circuits. And these resistors that have some resistance are quite useful in putting into different kinds of circuits to be able to drive certain currents that you want. All right. So the way that we're going to do that is kind of a very simplified model of a resistor. So what we're going to do is we're going to say that inside of a resistor, which a thin wire is one example of one, that there is an electric field. And that electric field exists over the extent of that resistor, which might have some length L. And as a result, there is a potential difference across that resistor. And in this case, we're going to just worry about its magnitude. Right? So this is sort of hearkening back to our definition of the electric potential, which is minus this line integral. Right? But we know that the electric field inside of that resistor is going to be constant. It has some length. And so this is the potential difference that we expect across it. And as a result, we can relate the electric field to that potential difference by dividing it by its length. We can go back to Ohm's law, or we can go back to this idea of the current density and relate these quantities to the current density. And then going a little further back, we can relate this to the current itself by multiplying the current density by the area. So that now, it's quite typical to collect the terms that we have that are not the potential terms into a single combination and to write down a relationship here, which is namely that the current is equal to a potential difference divided by a quantity that we will call the resistance. And you can see sort of why we call it the resistance, because for a given potential difference across the resistor, right, for a known value there, the higher the resistance, the less current we get. This is where this idea of resistance comes from. Really what we know is that the electric field in there is going to be really big, and the velocity of those charges is going to be really high, but overall the whole current throughout the circuit would reduce with a higher resistor. Now that collection of quantities is exactly equal to the length of the resistor itself divided by the conductivity times the area. And so this guy here gives us the relationship again between micro quantities and measurable micro quantities and measurable macro quantities. The resistance is something that we can measure with a voltmeter. We have to set up experiments to measure conductivity, but the length of the resistor and its area are also measurable quantities. So what we've done in this video is basically connect in a variety of ways microscopic quantities and macroscopic quantities, and also ones that are measurable in the laboratory compared to ones that are inferable from those measurable quantities. And ultimately what we were able to talk about is that resistors, things that produce different kinds of currents based on the potential difference, are modeled as having longer ones creates more resistance, having bigger ones, wider, creates less resistance. If they're more conductive, they have less resistance. This all kind of fits with our understanding of how this should work, right? It's going to take more energy to push over a longer distance. If you have a bigger tube, you can get more stuff through. And if it's more conductive, it's more easy to move those things through.